So, we are going to talk about martingales today. So, what are martingales? We cannot immediately approach that. Martingales are particular type of stochastic processes. If a stochastic process behaves in a certain way, we will call it martingale. In order to understand martingales, we need to first talk about the notion of a filtration. Of course, in any discussion that we begin with, always keep in your mind that even if I do not mention it, underlying everything is the following probability space. Okay. Now, what essentially is filtration? Filtration is the part, what happens is that as a random experiment progresses and new information becomes available, you know which part of the sigma algebra you already know. So, some part of the sigma algebra would be completely revealed. So, some part of f, a subset of f would be revealed once we start getting more information. For example, I throw a fair coin. So, if I throw a fair coin, there are 8 possibilities. Okay. So, let me write down what are the 8 possibilities. This is 1, or we can have all heads, head, tail and then head, head, tail and tail, tail, tail and head, tail, head and head, tail, head, tail, 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 tail. These are the 8 possibilities if you throw 3 coins in or 1 coin thrice in succession. So, you are doing a repeated experiment. Now, suppose I know that the first coin, I tell you, okay, suppose I do not allow you to see the experiment, I am conducting the experiment, and I tell you, okay, the first coin has turned out to be head. Okay. Then what are revealed to you? What events are revealed to you? If the first coin is head, is the situation is this one, means you know if the first coin is head, the only possibilities now are the following. Sorry. So, once I know that the first coin is head, there are only these possibilities that can occur. Or maybe if the first coin is tail. So, if the first coin is head, then these are the possibilities that can occur. If the first coin comes out to be tail, then these are the possibilities. So, if the first coin, the outcome of the first toss is known to me, then given any omega, if you give me any omega, any sequence of 3 tosses, I can tell you whether this will be revealed or this will not be revealed, this will be an outcome or this will be not an outcome. Suppose I tell you, okay, the first coin is toss, the head has come out to be head, and you say, okay, can tail, tail, tail come? No, the tail, tail, tail will come in the complement of this AH, this is the complement. So, what we have done, we have essentially segregated this thing, separated this out, made a finite division of these two. So, given any omega now, any omega does not belong to the empty set, every omega is belonging to the whole space, sample space, which means the sample space and the empty set is always revealed. You know that either there will be nothing or there will be some everything basically. But the interesting part is that now given an omega, I can tell you whether that event will now occur or will not occur. I have the information. If you say first toss is actually head, I can tell you what will actually happen, what are the next consequences, any of those 4, right. If you say okay, what about THT, can these consequences there will be there? No, it cannot be. So, if you look at it, the following sets of the sigma algebra F is now revealed, which I called F1, which is so if I have a knowledge about the first toss, these are the sets of the sigma algebra which is revealed, and this itself, F1 itself is a sigma algebra, because it follows all the rules of the sigma algebra. Because if you take the union of these two, it will become omega, right. If you take the intersection, it will become phi. If you take the complement of AH, it is AT, complement of AT is AH. So, this is a sigma algebra. So, this part of the sigma algebra, so this is of course, you immediately see that F1 is a subset of the sigma algebra F. So, part of the sigma algebra gets revealed when some information is revealed. And the next stage I said okay, good, I tell you what has happened in the second toss, then I will have more finer revealing. I can again partition this into more finer parts. And basically I am breaking up the space F, the sigma algebra F. So, if you tell me that, so what can be the second toss, like either both can be head first, head and then can be tail, or the first can be tail, the second can be head, the first can be tail and the second can be tail. So, if I tell you what are the 2 consecutive things, you know what can occur now. If I have the knowledge of what is also the second outcome and also I know both the outcomes, I know what are the occurrences. So, here it will be this, nothing else but just augmenting with head or tail, that is all. So, we have made more finer divisions of this basically. So, I know if you say that the first coin is head and also the second coin is head, if you say the second coin is head, so these are the 2 things that can happen, any one of the things can come. Second coin is head because the first coin is could be head, could be tail. So, any one of these 2 things can come. Now, you see, can I now make some sigma algebra out of this information? So, this sigma, that sigma here for example, this sigma algebra totally encodes the information that the first toss is known. If I know the second toss, can a sigma algebra be constructed which can encode all the information? So, of course, you should have once, if you want to construct a sigma algebra, if they are all inside that sigma algebra, then all this has to be also part of the sigma algebra, because ACHH is not any one of them but this whole, the union basically. So, you basically do not have to, when you construct the set, you do not have to write the union of this, union of this, union of these 3 or union of any of the 3. because that is the complement of the remaining. So, you can take the complement so that is it. So, you take the complement and that is, so you take the complement. Of course, you have to take some unions also. For example, if I take this union, such a union does not, such a union for example does not appear in any one of these sets already known. For example, if you take this set and take their union, there is nowhere I can find anything, right. But if you take this set and take their union, then this set is 80. So, I do not need to bother about the union of this set, but I have to bother about union of these two sets, which were not there to create the sigma algebra. You see, AH and AT is anyway revealed even if I know the second choices. The first choice must be either head or tail. So, these are already there. So, whatever is known at the first stage will always be carried on to the second stage, because they are anyway revealed. For example, if I take the union of these two and take the complement of that would anyway give me AH. So, AH and AT anyway will continue to be revealed, right. So, essentially if I want to construct F2, you see how fast the size of the cardinality of this set will grow. So, AH and AT will anyway be there, okay. You will also have these sets AHH, AHT, ATH, ATT. Of course, then you have to line up their complements. Okay. Now, you can combine this with this, do not combine this with this, because this with this will give you AH. So, it is already there, so you do not have to show that combination. So, A HH union A TH must be there, must be considered. A HH union A TT must be considered, because they will not form anything which is already given. AHT union ATT must be ATH must be considered, these two, and AHT union ATT must be considered, means those things which do not appear at all. You see your from just 4 elements here, you have increased to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, sorry 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15, 16, 17, 18, just blowed up actually. Now, it comes F3, all is known. All is known means F3 means I know all possibilities. So, I basically know the whole sigma algebra F. So, F3 at the third, if I know all the coin tosses are known, then F3 is nothing but F, and that will have 256 possibilities, 2 to the power 8 combinations, because there are 8 possible elements in the sigma algebra. So, what I have Now let us talk about what is F0 then. F0 means when nothing is revealed to me, then I have only two choices, either nothing will happen or every possible choice might happen, right. So F0 consists of just, so this is under no information, this is under one information, that first toss is something, this is under more information, the second toss is revealed, and this is under the third, you have revealed everything. So everything is revealed. So which means if you look at them, you have f of 0 belonging to f of 1, belonging to f of 2, belonging to f of 3, belonging to f. So f of 3 is equal to f, you don't have to write f of 3 subset of f, but equal to f. So what I have done is a chain of sigma algebras each containing the other. So as time evolves, more information is revealed, you know more about the structure of the sigma algebra. So such a sequence of sigma algebras, which each of them are subset of the original sigma algebra and each of them are bigger than the previous one, such a thing is called a filtration, which we can obviously formally define. So this is in a very discrete setting, you can define filtration in the following way. So this definition I have given from the book of Stephen Shrieve's book called Stochastic Calculus for Finance. Now observe what I want to say. So if you have sigma f p and let t be a number greater than 0, assume that for t greater than equal to 0, less than equal to t, there exists, this is a symbol of there exists, a sigma algebra Ft. So whenever we are going to write continuous things, we will put it Ft instead of this t, just to differentiate between the discrete thing and the continuous thing. When we write the discrete thing, we will write it as a lowered index, and when we write the continuous thing, it is as if it is a function. So there exists a sigma algebra Ft such that whenever I have s less than equal to t, f of s must be contained Ft such that Ft is contained in f, and whenever s is less than equal to t, it will f of s would contain f of s will be contained in f of t. So f of t will contain f of s. So this condition has to satisfied. Then if these are all satisfied, then the family of sigma algebras Ft, where t is from 0 to t, is called a filtration. Filtration associated with with the probability space. So, it might, the definition might look tricky, but I think you can go and read it up in books, or just think about it a little bit, just think about the definition. You can, if you want, rerun the whole lecture, so you can see it how many times you want, so that you get your concepts cleared once for all. So, then we are going to talk about something called a stochastic process adapted to the filtration. So, given a stochastic process x t, say is of this form. So, this is a stochastic process given to you. We say that this x t is adapted to the filtration f t if x t is f t measurable. So, all these are all random variables. For every t between 0 to t, x t is some random variable adapted to the filtration if x t is f t measurable, and x t measurable, that is x t inverse of b belongs to f t for all Borel set b in R. Okay. This is the meaning of an adapted stochastic process. Martingales are special type of adapted stochastic process. So, first we will talk about discrete martingales, and then we will talk about continuous martingales. Do not get too much bother about their properties right now, except the one which we will require. So, suppose you have a discrete filtration, so Fn, so 0 to say n equal to 0 to capital N. Why I am using a finite class? Because I am essentially talking about finance. In finance you have a trading horizon, trading time. So, trading starts at 0 and ends at t. So, ends at time n. So, that is why I am taking the simplest definition. You can possibly take n equal to 0 to infinity, that does not matter. You can have a stochastic process which is infinite. Stochastic processes are nothing but sequences of random variables, where the indexing is actually over time. Fn is a given filtration, and then you have xn n equal to 0 to capital N, a stochastic process adapted to this filtration. So, you will hear this term adapted to this filtration repeatedly after this. stochastic process adapted to the filtration Fn. So, now we will call Xn to be a discrete martingale if a conditional expectation of the random variable at n plus 1, that is x n plus 1, having the information till time n x n. So, how it is related to gambling possibly? It says that the stochastic process is a martingale if your expected payoff at the n plus 1th move is same as whatever payoff you have received at the nth time, provided you have only information up to nth time, which is that fact. You do not know what will happen at n plus 1, it is uncertain. Up to nth time you have information, you know that this is x n is what I have got, is a random variable or the random process which was revealed when I had done the gambling at the nth instant, but when I am going to do it at the n plus 1th instant, conditioning upon the fact that this is known, then this is my answer. And I cannot expect to improve. Once I improve, then I call it something like a super martingale. If I do bad, then I call it like a sub martingale. So, this is what one should expect, that I can only expect I will do as much as I did last time. My payoff would be as much as I had last time, nothing else. Of course, you can ask that this will go on basically. N minus 2 f f n plus 1, this will again become x n plus 1. So, this is what is known to me. Now, I will put this fact here. So, let me see what I get out of this, some little game with conditional expectation. So, this itself is again this. So, if a scenario is revealed at the n plus 1th time, then what I expect to get for a given scenario is same as what I would get at the previous time. That is the meaning of, I cannot expect something more, I have to remain at status quo, that is what I can expect. So, if I am putting this fact here, then by using the Tower law of conditional expectation, because f n plus 1 is a larger sigma algebra than f n, I can write this is nothing but the conditional expectation of x n plus 2 conditioned on f n. So, it does not matter whether it is now n plus 2 or n plus 5 or n plus 6, you can. So, this is an application of the Tower law. So, it does not matter what is your xn, after xn, however large n you put here, put any m, does not matter, m is n plus 5 or n plus 100 or n plus 10. If you just have information up to n level move, whatever x m you put, m is any number bigger than n, conditional expectation of x m, conditioned on the fact that I know only things up to n, is nothing but x n. That is the meaning of the Martingale. And this idea, this fact that does not matter whatever you put here, if you just know up to fn, you know you can only expect what you have got up at the nth level. And this fact, this beautiful fact, has some beautiful properties, and so this idea actually allows you to also look into the continuous case. If you have a continuous martingale, you just have to write this. So, a continuous stochastic process x t given the filtration f s would remain to be x s whenever s is less than equal to t. So, this is the meaning of a this is just the definition of a continuous martingale. Okay. Now, I will just tell you one property is that it does not matter whatever be your position. If you take the expected value, just calculate the expectation of any one of the random variables, that is the expectation for each of the random variables. So, you have the stochastic process x1, x2, xn like this. So, x1, x2 dot up to capital Xn, x of capital N. Then if you take each of them as separate random variables and take their expectation, provided that this sequence is a martingale, then every random variable will have the same expectation. So, this calculation can be done very simply. I will just do it on the top and end our talk today, and tomorrow we will start some lovely thing called Brownian motion, and that is the hardcore stuff, because Brownian motion needs to be known, because that will allow us to model the behavior of stock prices in a financial market, in a stock exchange possibly. So, here we just do it in a very simple way. So, take expectation of xn. So, this, okay, I am just writing, maybe I should write in a much more different way, but okay, I am just writing in a standard symbolic way. So, this is nothing but integral but by the very definition of conditional expectation, the law, when you do it for the general case, general sigma algebra Fn, not the one generated by a partition, you know you have to use this partial averaging idea, that is essentially you define it in that way. And this is nothing, this one is nothing but xn plus 1 Tp. This is the definition of conditional expectation for the general sigma algebra. This is called the partial averaging, and this is nothing but expectation of xn plus 1. So, it does not matter. So, which means if x0 is equal to x1 is equal to E of x2. So, so what you finally get is E of x0 putting n equal to 0, that is equal to E of x1, that is equal to E of x2 . So, with this lovely property of the martingale, we stop our discussion here, and tomorrow we are going into this wonderful stuff called Brownian motion, and we will take our discussion off from there. Thank you.